Okay, so today we're going to be talking about asymptotes and wholes of rational functions. So, when you have a rational function, y equals something over something else, and it's rational, it may have what we call asymptotes. So, an asymptote is a value that a function approaches but never reaches. So, we're going to be focusing on two different kinds of asymptotes today. And those are vertical asymptotes and horizontal asymptotes. So basically, if we make a graph, the y-axis and the x-axis, we might have a function that could look like something like this. Let's say we have a function that looks something like this. So basically, we can see that as the x value approaches infinity or keeps getting larger and larger, we can see that there is some line that it is approaching. And with these dotted lines, we can show this line. So it seems to be approaching a value of y equals 1. So that is an asymptote that is approaching. That is actually a horizontal asymptote. Basically, as x approaches infinity, it will never reach 1, but it is just approaching 1. So that would be a horizontal asymptote. There we go. And we can also see a vertical asymptote. This graph is approaching. It looks to be a value of x equals 1. A vertical asymptote. So it's important to understand, to be able to tell if a certain graph will have vertical asymptotes, horizontal asymptotes, and whatnot. So we're going to see a couple examples of how to identify if there's vertical asymptotes, horizontal asymptotes, and also how to find what these asymptotes are based on just by looking at a function. So our first function we're going to be looking at is y equals 1 over x minus 1. So I have written down, there's two separate tests we need to do. One's for vertical asymptotes, the other's for horizontal asymptotes. For vertical asymptotes, we set the denominator equal to 0 and solve for x. So as you can see here, I set the denominator equal to 0, x minus 1 equals 0, which is the denominator, and then you solve for x. So you just add 1 to both sides, x equals 1. So there should be a vertical asymptote at x equals 1. Boom, done. Now we look to horizontal asymptotes. So horizontal asymptotes, and finding them, basically we just need to look at the degree of the numerator and the denominator. So as you can see, the degree of the numerator is 0 because there are no x terms, and the degree of the denominator, well, the degree of the denominator is 1. We don't see a 1 here, but x is equal to x to the 1. It's basically the same thing. So the degree up top is 0, the degree on the bottom is 1. So the numerator, the degree of the numerator is less than the degree of the denominator. And we have, if the degree of the numerator is less than the degree of the denominator, then there's an asymptote at y equals 0. So horizontal asymptote at y equals 0. And now using the math whiteboard, we can basically check our answer. Oops, here we go. We can check our answer. So we said there should be a vertical asymptote at x equals 1. It appears to be so. And we said there should be a horizontal asymptote at y equals 0, which it appears to be so. So we're just going to do some other examples, and basically we're just going to do both these tests and see what we find. And then hopefully we can do it without these boxes up top, and we can just remember how to find vertical and horizontal asymptotes. So this one, y equals 2x plus 4 over x minus 5. So first we're going to test for vertical asymptotes. So we need to set the denominator equal to 0. So it's a pretty simple one. X minus 5 equals 0. Solve for x. What are we going to do? Well, we're going to add 5 to solve for x. X equals 5. So there should be a vertical asymptote at 5. So next, we're going to look for how to find these horizontal asymptotes. So it appears that in this function, we have the numerator being a degree 1, because remember there's a hidden 1 above the x in the exponent spot. And the denominator is also a degree of 1 with a hidden 1 in the exponent spot. So what do we do then? Well, if the degree of the numerator is equal to the degree of the denominator, then you take the two highest degree terms, which would be on top 2x and on the bottom x, and divide the coefficients. So what it means by this is basically you want to do 2x over x, which simplifies into 2. So there should be a horizontal asymptote at y equals 2. Now we want to know why this is. So typically with horizontal asymptotes, if we were doing limit notation, it's the limit, limit as x goes to infinity. So imagine we plug in, well, not infinity, but a really, really, really large number. Let's say we plug in 1,000. So if we plug in 1,000, on the top at least, it would be 2,000 plus 4, 2004. Over, plug in 1,000 at the bottom, we would get 995. And imagine we plug in an even bigger number. We plug in 1,000,000. We would get 2,000,004 over 999,995. So basically you can see that these two terms, the lesser terms with the lesser degree, they don't really matter in the end. The only ones that matter are the highest degree terms, because those are the ones that will affect the graph the most. So as we plug in bigger and bigger numbers, it will eventually just go to the highest degree terms. So that's why we only factor in, the highest degree terms while we find the horizontal asymptotes, if the degrees are equal. So if we ended up plugging in infinity, this would go to 2. So that's why we have a horizontal asymptote at 2. Hopefully that makes sense. And we can see that. We put it in the graph. Here, let me zoom out a little bit. Oh, a little too much. There we go. So we can see here, if we look for a horizontal asymptote, yep, looks like it's around 2. If we drew an imaginary line, both of these approach 2. And a vertical asymptote, it appears, yep, x equals 5. We did good on that one. Now we can move on to kind of a more difficult example, but still doable. We got this. So let's check for vertical asymptotes again. So we want to set the denominator equal to 0 and solve for x. So notice that there are two different things we need to set equal to 0 here. We need to set x plus 3 equal to 0, and x minus 2, there we go, equal to 0. We solve for x for both. X equals -3, and x equals 2. So there should be vertical asymptotes at x equals -3 and 2. So we'll check that, but first we need to find, what are the horizontal asymptotes? So this one, at first you might think, well, the numerator has degree 2, and then both of these are degree 1, but we can combine these two terms. So if we combine them, we would get something that looks like this. We can just write the numerator again, 2x squared minus 5. But now we can combine these into x squared. You got minus 2x plus 3x. So we'll just get a plus x. Minus 6. So we can see now that, once again, the degree of the numerator on top is equal to that at the bottom. So we take the coefficients, 2 over 1 equal to 2. So there should be a horizontal asymptote at y equals 2. Alrighty, let's see if we were right. Let's move this down. So we can see here there is a horizontal asymptote once again at 2. We got that right. And a vertical asymptote at x equals 2, correct. And a vertical asymptote at -3. Boom, correct. So now that we know how to find horizontal and vertical asymptotes, we're going to look at another discontinuity, which is a hole. So I have a hole is a point in the graph where the function is not defined. So holes and asymptotes, or vertical asymptotes at least numerically, are very similar in the actual function, but visually they're very different. You'll see what I mean by this. But basically a hole, let's say we have a function and we have something that looks like, could just be like this. So let's say, or actually here, that doesn't work. Let's try this. Say something like this. We have a function like that. And a hole would be a point right here where at that exact point it does not exist in the function. But zoomed out, it appears that it would exist. But if we zoom in, and we zoom in to a great degree, we would see that it actually does not exist in the function. So you'll see what I mean by this. So identifying a hole. So if the numerator and denominator share a common factor, then the graph has a hole. So basically what I mean by share a common factor is, you can see in this problem we have on top x minus 2 times x plus 3, and at the bottom we have x plus 3 divided by x plus 4, or times divided by x plus 3 times x plus 4. So we can see that the top and bottom share a common factor of x plus 3. So we would do this. Here, let me write this out. X minus 2, x plus 3 over x plus 3, oops, whatever, x plus 4. So you can cancel these terms. So if we set that equal, our cancel term equals 0, we would get x equals -3. So basically the test for a whole is if there are two of the same terms on the top and the bottom, or two of the same factors on the top and the bottom,